Hi. So in this video, we're gonna use the convergent sequence to define the closed set. Okay. So previously, we know if we're gonna say some set S in Rn that is a closed set, so we simply have a definition for that, such that the complement of S, so Sc, that would be an open set, right? So that was the original definition. So today we'll try to have another definition, okay? Um, and this is sort of definition, but we can actually prove that, right? So this is more like a proposition. Okay, so let's see. So we're gonna say this set S in Rn that is closed if and only if, so we have both two directions, for any convergent sequence. Okay, so this xi from 1 to infinity, so that'll be a subset of S. So for any convergent sequence that, with the limit of this sequence, so that'll be this x, also in Rn. So, and we always have this x to be an element of S. Okay, so essentially it's saying that if some set S in Rn is closed, then we can have that limit of some convergent sequence. Actually, that is for any convergent sequence, right? Inside of this S, then we have that limit, and that is included, or that is an element of S itself, and the other direction that is also true. Okay, so this is the sort of the proposition, or you can call this definition, but we're gonna prove that. Okay, so this is more like a proposition. Okay, so good. So let's do this. So here we have those two little pictures, right? So which are showing the interpretation of this result, right? So if the set S is closed, and we can see that we can always find those any of those sequences inside of S, then we have those limits that are on the inside of S, okay, or on this boundary. But if that S is not closed, and then we can see that those dashed lines, right? Those parts are not included in the set S, and then it's not for any convergent sequence to be able to find such a limit also including S, right? Because here we have this limit on this boundary, but that is not included in S because this part is not closed, right? Okay, good. So those are some pictures that are pretty straightforward for us to understand this. So now let's gonna try to prove this on both two directions theoretically. Okay, good. So the first direction, right? So this is gonna be the proof. So we're gonna try to prove this direction. Okay. So that'll be the only if, right? Okay. All right. So for the only if direction, so we're gonna first suppose that this S in Rn that is closed, right? And then we're gonna from that to derive the other statement, right? Good. So now let's do this. So suppose S is a closed set. Okay. All right. So we're gonna prove by contradiction. Okay. So this would be by contradiction. Okay. So from this starting point that S is closed set, then we're gonna find some contradiction that is contradictory to the other statement, right? Where we have some limit also inside of S. Okay, so then we're gonna consider, okay, any convergent sequence. Consider any convergent sequence. Okay, so this would be, we call this also as xi from 1 to infinity. Okay, and that's a subset of S, and let's call the limit as x. Okay, so but here let's say this limit is in the complement of S in Sc. Okay, all right, so this is something that we gonna start with, because we want to use the contradiction. So here we simply assume that we can find so any of those convergent sequence with some limit that is not in S, but instead it is in Sc, right? So this is not what we have in the original statement, right? So this is gonna be something wrong, right? And we're gonna try to prove that this is wrong by some contradiction that we're gonna find later. Okay, so that's the idea here. So how do we do that, right? So then for any there exists some epsilon. Okay, all right, so we're gonna have, okay, so this is because we have this S is closed, right? So the Sc, the complement of closed set, that will be open. Okay, so by the openness, so maybe we should write the other way. So since S is closed, so Sc is open, right? So by the definition of open set, then we can have this following statement, right? So there exists some epsilon, and we have that open epsilon ball, right? And centered with this X. So that's going to be a subset of Sc. Okay, because that, so this is simply just the definition for the open set, right? Good. So then next, so now we have this epsilon ball, but the center is actually at this X, this point X. But remember that this X is in Sc, right? So that's something we're gonna assume perhaps that is false, right? Okay, and then for, okay, any of those i's, so because we have, okay, now we have those, remember that those xi's, they're in S, okay? It's just the limit is not in S, but those xi's, they're all in S. So xi is in S. Okay, so xi is not in Sc. Okay, and it means that, okay, well, it's because this epsilon ball centered with X, that is in Sc. So since xi is not in Sc, so xi must not be inside of that ball, right? So, and also the same for xi is not in this epsilon ball with X. Okay, so it means that, so now this is pretty weird, right? So there must be some problem. So this means that this, all those points from 1 to infinity, all those xi points, they're even not inside of this epsilon ball of X, right? So then this X is not some, this is X is, this is not a valid, or it's not a true limit, right? So because it's even not inside of all those X points, they're not inside of this ball, right? So they're too far from each other. Okay, so mathematically, so that is okay for any I. So this means that okay, so the Euclidean distance between those xi's and x, so this is gonna be greater than this epsilon. Okay, but this is the problem, right? Because we said that this is a convergent sequence with the limit of this x. So this x, it has to be the, so this is by definition, right? So that we defined previously. So this x is the limit of this convergent sequence. But now you're telling me that this limit x is always very far from any of those points, right? So it means that this is not any limit, right? So this is not a valid limit because those this limit x, sort of quote unquote, this limit x is not pretty close to any of those points, right? So for any of those xi points, the distance between xi and that limit x, so-called limit x, this distance is too far, right? Which is greater than this epsilon. Then this is not satisfying the definition of the limit. So that would be a contradiction, right? So x is not, okay. So we say that x maybe we should write that, so this leads to the contradiction that x is the limit of that sequence. Okay, so you know that, so that's simply the sequence. Okay, all right, so that would be the first direction, right? Where we use the contradiction to show that if the set S is closed, then for any convergent sequence, okay, we always have that limit x to still be inside of the set S. Okay, and here we show by the contradiction, we simply suppose that there's some limit that is for any of those sequence with the limit that is not inside of this S, but actually we assume that this is inside of SC, the complement of S. Then we found this problem, right? So this contradiction. Good. So that would be the first direction. Okay, so now let's try to prove the other direction with the if direction. Right? Okay. Good. So for the if direction, so a easier proof that would be to use the contraposition. Okay. Or you can call that as contrapositive, right? Those are essentially the same thing. So, okay. So by the contraposition, okay, remember that we're gonna show the backward, right? The other directions. So it means that if we, for any convergent sequence with the limit, we have that, then this S is closed. Okay, so the contraposition of this statement, that would be, we're gonna start from supposing that is S is not closed, right? Then we're gonna show, by contraposition, we're gonna show that the negation of the latter statement, right? So that would be this direction. Okay, good. So now let's start. So suppose S is not closed. Okay, so but do not confused by two very similar things. So not closed, it is not exactly the same as open, right? All right, so and just see the example that we have here, right? So this S is not closed. right? So it's just maybe half or like two thirds is closed, and one third or like half is open. But the opposite of this, so yeah, so we cannot say that the a not closed set is open, right? We can see obviously that this set is not open or not closed, right? So that's the problem. Okay, so we suppose S is not closed, and simply it's meaning that S is not closed. It's not saying that X open, right? So that's very important. So what we're gonna do, or we're gonna show that there exists a convergent sequence, okay, from 1 to infinity inside of S as a subset of S with some limit X that is not inside of S, okay? Because remember that the negation of some statement with any, then we're gonna, by the negation, we're gonna have the exist statement, right? And then make the other direction for the statement, right? So that would be the negation for the statement, right? So suppose S is not closed, so we want to show there exists a convergent sequence. Okay, so xi from 1 to infinity as a subset of S. So exist, now we convert the any to exist, but we're also gonna have the negation, right? So with the limit X, now this X is not in S, okay? We do not say that X, so by the negation of X in S, so the negation that will be X not in S, right? But we cannot say that the negation of this, so this is a valid negation, right? But we cannot say that the negation of this is, let's say, X in SC, right? So this is not okay, okay? All right, so that's what we want, right? Good, so how do we do that? Okay, so let's start from the starting point, right? So suppose that S is not closed. Okay, so since S is not closed, okay, then what we can say something about the complement of S, that SC is not open. Okay, so that's something that we can say, right? Although we cannot say that S is open, but S is not closed, but we can say something about SC that is not open, right? Okay, and this is pretty easy to show, right? You can do this by yourself. So there exists some X, okay? Then in this SC, because that is not open, then there exists some X, okay, in this SC such that, okay, for any epsilon, this epsilon ball centered with X intersects S that's not gonna be empty, right? So we can always have something since this S is not open, right? So we're gonna have, and then there must exist some point X in this SC which is not open, right? So if we simply take the intersection of this epsilon ball, so no matter whether this, how big is this epsilon, right? For any epsilon bigger than 0, so we can always find some element, right, which is not an empty set. Okay, so that would be halfway down. Okay, so then we still need to finish this proof by show there exists some convergent sequence, right? So inside of S, but the limit is not in S. Okay, so how do we do that? So we simply constructed that sequence. Okay, construct. So we're gonna construct this sequence by ourselves. Okay, so it's gonna be xi from 1 to infinity and in S. Okay, good. And we want to show that here, so this xi is, so this will be an element, okay, of a boss, but we have this radius as 1 over I, okay, with center x and intersect S. Okay, so we simply construct this such a sequence, okay, where that is a subset of S, okay, and for each of those xi, that would be an element of the intersection of S with such ball, but with the center x with radius of 1 over I. Okay, so here this I is from 1 to and so on and so forth. Okay, so and then what we have next, okay, so that's gonna be for any epsilon, okay, so there must exist some number, let's say capital N, okay, so there must exist, so and there must exist some number N, capital N, and for any I which is greater than or equal to N, we have the Euclidean distance between xi and x, okay, which is smaller than this number epsilon. Okay, so from here we can see that this x, that's something that we want for this limit of this convergent sequence xi, right, from 1 to infinity. And we also know that this this x, this point x, that is inside of this SC, right? So that's something that we want. That is not inside of S, right? And then this completes this proof. Okay, good. So then we have shown from both directions of the statement that where we use this convergent sequence to define the closed sets, right? But that actually this is more like a proposition that we can prove. Okay, so that'll be everything for this episode. Good.